Okay, so we're going to take a look at example 2 on the top of page 89 in the workbook. And this is another question where we're given a series and we're being asked to kind of explore the convergence of it, make an educated guess as to whether it converges or diverges. All right, so just to get a feel for this, let's write out a few terms in this series. So remember, we're starting from the number n equals 1. And if you take 1 and plug it into the formula n over n plus 1, you're going to get 1 over 1 plus 1, which is 1 over 2. That's the first term in our series. Then move on to the next value of n is 2. We're going to get 2 over 2 plus 1, which is 2/3. And then 3/4 and 4/5 and so on. Okay, that's what the terms in our series look like. Okay, and again, to explore the question of convergence, we're going to look at partial sums and just see how they're behaving. Okay, so we'll start with S1, which again just represents the sum of the first term in our series. The first term is 1 over 2, or 0.5. Okay, then we'd move on to S2. That just represents the sum of the first two terms in our series. So 1/2 plus 2/3. We'd add those two numbers, which you can do, and we get 1.17. Okay, let's do one more partial sum here. S3 would be the sum of the first three terms. Okay, and if you add up those three numbers, you get 1.92. And the question we're trying to answer is, as we look at those three numbers, does it look like they're approaching something or going off to infinity? Okay, well, I don't know what your opinion is, but for me, that's not quite enough data. I'm not really sure whether we're going off to infinity or converging based on those three numbers. Okay, so here's where it's useful to maybe go to a program like Mathematica and ask it to add up a whole bunch of terms for us. All right, so I went to the computer and had it add up the first 100 terms in this series, and here's what it came up with. 95.80. Okay, quite a bit bigger than the first three numbers that we looked at. Okay, and I'm going to show you two more partial sums. Again, these came from Mathematica. And what do you think about convergence now? There seems to be some evidence that these sums are going off to infinity, so we might be looking at a divergent series here. Okay, to get a better idea of what's really going on here, what we might pay attention to, though, is the gap between these numbers that we're seeing. For example, between 95.80 and 96.79, you see how that's distance between those terms is 0.99. That's pretty close to 1, which is basically like saying that when we add the 101st term in our series, it's going to be about 1. It's going to be 0.99. And we get a similar behavior between S101 and S102. That's telling us that the 102nd term in the series that we add is 0.99, or about 1. Okay, and where does this number 1 come from? Okay, well, it actually comes from the n over n plus 1 that's in our series. Okay, let's just explore what would happen if we took the limit as n goes to infinity of that n over n plus 1. Okay, well, if you used L'Hopital's rule on that, you would get 1 over 1. Okay, and so the limit would turn out to be 1. What that's really telling us is that if we go far enough out in the series, we get to a point where every term that we add is like adding 1 over and over again. Okay, so I want to do just a little side experiment here. Let's go back to the series that we started with. Okay, we already showed what the first few terms look like. But what that limit above tells us is that if we go out far enough in our series, the terms that we add are going to approximately be 1. Not exactly, but very close to 1. Okay, so here's my question to you. What happens if you take the number 1 and add it to itself infinitely many times, over and over and over again? It's going to go off to infinity, isn't it? okay, which tells us that this series has to diverge. Okay, let's see if we can put that all into words here. Okay, so just kind of summarizing and pulling all of these observations together, this means that for large n, the partial sums increase by about 1. Okay, and that's just kind of restating this limit that we calculated above. We get to a point where we're adding something close to 1 every time we add a new term. And what that means is that since we do that infinitely many times, this sum has to go off to infinity. All right, so we can finish this statement by saying because we add about 1, infinitely many times, the series has to diverge. It goes off to infinity. Okay, and this basic observation that we made leads us to our first test for series convergence, the theorem that you see right below. It's called the divergence test. And it says that anytime you're in the situation where the limit as n goes to infinity of the nth term of your series is something that's not equal to 0, the series is going to diverge. Okay, in our case, we took this limit and we got the number 1. Okay, this theorem says that there is nothing special about the number 1, okay, other than the fact that it's not 0. Okay, so if you look up here where I'm circling, even if that 1 had been 1/2, let's say, 1/2 is not 0, and so if you add 1/2 to itself infinitely many times, you're also going to get infinity. And so we should get the same conclusion of divergence there. Okay, so this is a nice little test to convince ourselves that a series diverges. Okay, now I want to leave you with just one caution when you're using this test. Okay, what if we took the limit that you see in the test above and we did get 0? What would that say? Okay, well, it's tempting to think that if we take this limit and we do get 0, then that must mean that the series converges. That would be the other way around. Unfortunately, that turns out to not always be true. So we would have to complete this statement by saying this does not guarantee that the series converges. It might converge or it might diverge. The point is we would need a different convergence test to determine whether or not it converges or not. So the divergence test only is useful to us if we take this limit and we get something that's not 0. Okay, and we will